and this is our last video for the whole of the AS course on equilibrium. You need to make notes on this for Friday when you're coming into school. It's quite a short one, and a lot of it is revision from GCSE for those of you who did triple. Those of you who didn't want to pay quite close attention here. So, let's start off by thinking about what an equilibrium. Well, actually, first let's look at the specification points. This is what we're covering. You see there's only 4 and they're not too difficult. They explain from given data the importance of, in the chemical industry, of a compromise between chemical equilibrium and reaction rate. Is probably the longest bit we're going to have to look at in terms of an exam skills thing. So let's have a look at reversible reaction and work out what a dynamic equilibrium is. Here we have nitrogen dioxide becoming nitrogen peroxide. Now, if we look at this reaction, we can see that if I start off with a load of nitrogen dioxide, I'm going to make some nitrogen peroxide quite quickly. But then as I make the nitrogen peroxide, I increase the nitrogen peroxide concentration, meaning I start making nitrogen dioxide again. Let's look at that in terms of a graph. Here we go. If we take nitrogen dioxide as A and nitrogen peroxide as B, if we start off with 100% concentration of nitrogen dioxide, we'll slowly decrease that and we'll slowly increase the nitrogen peroxide until we get to a certain point. In this case, we're at a point where about 40% of the volume is nitrogen peroxide and nitrogen dioxide, and 60% is nitrogen peroxide. Now, you'll see that what's happened is they've both leveled off at this point. That's because they've reached the point where they have the same rate. They each have the same rate of reaction, the forward and the back reaction. So if we look at a different graph, this is concentration, this is rate. So this is the rate of change of concentration. You'll notice the forward process and the reverse process have both reached the same rate in the middle. These two graphs don't have to meet in the middle because you can have different relative concentrations. That's called the position of equilibrium. How far to the right or to the left, how much of each one we have is the position of equilibrium. The fact that we're in an equilibrium means that we will have the same rate though for forward and reverse processes. So this guy called Le Chatelier came up with his principle for equilibria is that for a system in dynamic equilibrium like that one we just saw, when we put a change on the system, for example increasing the temperature, changing the pressure, changing the concentration of one of the reactants or products, the position of equilibrium will move to compensate for the change. So what does that mean? Well, let's imagine we change the temperature. This reaction, the reaction of chlorine with copper ions, is endothermic. So if we increase the temperature, the system will move in the endothermic direction to the right, because that decreases the temperature. Every time we go to the right, every time we go from this copper on the left to this copper on the right, then it decreases the temperature because it's endothermic. It takes heat energy out of the environment. So if we increase the temperature, we do more of those reactions, thus decreasing the temperature back down. So the position of equilibrium moves to the right, where we have more of this one than we have this one. What about changing the concentration? Well, if we increase the concentration of a reactant, it can therefore react further and faster. So the position will shift to the right to compensate for this increase. We'll have more of the product being made because there's more of the reactant at the start. So it moves to compensate for the change. We move away from where we've put the reactant and product in. And finally, pressure. So if we look at this is the equation for production of ammonia. You can see there's 4 moles of gas on the left-hand side and 2 moles of gas on the right-hand side. Each mole of gas, as we know, takes up 24 decimeters cubed. So we have more particles per volume over here than we have over here. So if we increase the pressure, the equilibrium is going to shift to the right to compensate, where we have a lower number of moles, therefore a lower pressure being exerted. Final thing to look at is the Haber process, which is a good example of all of the different things we've just been speaking about. So in the Haber process, you're trying to make ammonia. Ammonia is part of this equilibrium. So we set the conditions up so we can make the most amount of ammonia possible. Now, we take ammonia from the air and hydrogen gas from natural gas, and we mix them in a 1:3 ratio because that is the ratio they are in the equation. We then heat them up to 400 to 450 degrees C, have it 200 atmospheres of pressure and with an ion catalyst. Now, 200 atmospheres of pressure is quite obvious. We've just said if we increase the pressure, it's going to move to the right, increase our yield of ammonia because that's where the lower pressure is. Ion catalyst, that will increase the rate of both the forward and back reactions, but it means that things happen a bit faster. And 400 to 450 degrees C, that's not going to increase the yield because it's exothermic in the left to right direction. But what it will do is it means that we'll reach equilibrium faster. It's important to think about rate as well as about position of equilibrium. Now, the ammonia is then turned into a liquid, and that means that we've taken the products away, which means we'll move back to the position of equilibrium back to the right to be able to increase the yield further. Okay, year 12, I shall see you on Friday.